Hi, my name's Alex Apffel, and I'm an archaeologist in the Department of Anthropology at San Jose State University in California. And today I'd like to talk to you about some work we did in the field on the island of Nevis in the Caribbean and in the lab in collaboration with Professor Vuthea Chheang in the Department of Computer Science. Nevis and the neighboring island of St. Kitts constitute the Federation of St. Kitts and Nevis, a sovereign state in the Lesser Antilles and the Caribbean Sea. Nevis itself is a tiny island of only 93 square kilometers, but in the 18th century colonial period under British rule, due to its strategic location, the slave trade, and sugar production, it was the most valuable real estate in the Caribbean. However, long before European contact, Nevis was the home to an indigenous population. Although their origin is still a question, archaeological research suggests that the original inhabitants of the island were the Taino people who migrated from the northeast starting somewhere near the Yucatan Peninsula around 7,000 years ago. It's also possible there were influences from the South Amazonian basin and the Carib or Kalinago people as well. In any case, the original native Nevisians were a seagoing people who lived off the sea and built villages along the southwest windward coast. They made pottery and stone tools, and they buried their dead. They practiced agriculture and traded with other islands. Due to a combination of climate change, cultural resource sites related to the pre-contact Nevisians are literally threatened with being washed into the sea. Along the southwest coast, as you walk along the shoreline, pottery, pieces of stone tools, and even human remains are clearly visible, having been uncovered by weathering and rising sea levels. There isn't enough time to adequately excavate or even survey these sites from an archaeological perspective. So, in the summer of 2025, a team of archaeologists from San Jose State University, led by Professor Marco Menichetti, went to Nevis to try to digitally survey the area in as much detail as possible and create a digital twin of the area. During this time, we recorded 20 separate tracks as shown in the map on the right. These have been stitched together to form a nearly contiguous map of the coast for a distance of nearly 2 kilometers. There were really two goals for this project. In the first place, we wanted to generate a digital record that would capture the current state of the landscape with respect to sea level rise, erosion, and general condition as a baseline for longitudinal studies. We will be returning this coming summer in June of 2026 to repeat the measurements and record what changes have taken place. Secondly, we wanted to record in as much detail as possible the 3D record of as many sites as possible that could subsequently be reinterrogated either through manual inspection or through a combination of computer vision and machine learning to identify specific occupation sites based on artifacts and burial sites that are visible on the surface. These data could in turn be used to direct further investigation of the most promising sites or be used to generate maps of artifact and occupation distributions along the coast. In August of 2025, we worked in Nevis to digitally capture the landscape with two specific technologies. Our main tool was an Insta360 X4 camera shown in the center of this slide. The camera has two lenses, each which captures 420 degrees field of view, resulting in a complete sphere of coverage. To acquire data, the team members walked around the landscape in a rough grid pattern with transects spaced approximately 2 meters apart, holding the camera on the end of an invisible selfie stick. It's called invisible because the subsequent processing removes the operator from the final resulting video. Data is acquired in an app called Vista Capture produced by Cupix Vista. Acquisitions are done at 2 frames per second and 5.7K resolution. Note that the 5.7K is distributed across the entire spherical field of view, so is somewhat lower resolution than is ideal for artifact identification at this point. Each acquisition is limited to 20 minutes by the app. For some experiments, we used an alternative full video capture mode at 30 frames per second for comparison. As a second tool, we acquired photogrammetry data using iPhones and iPads of specific artifacts and structures using the Polycam app. In this case, two modes were used. In some cases, discrete images were taken from different angles and locations around the target to capture as complete a view as possible. In other cases, a guided LiDAR acquisition was done, in which the app essentially painted the areas that had been acquired to show the operator what was complete on the object in question. Finally, specific artifacts were photographed in situ with both iPhones and 35mm cameras to document important artifacts. Once 360 camera data was captured, it was transferred from the camera to the iPhone running the Vista Capture app, and then subsequently uploaded to the Cubix Vista platform in the cloud. After processing, the reconstructed landscapes are available to be reinterrogated as shown in the true screen capture shown in this slide. This interface typically has two windows available to work with. Referring to the figure on the left, there's an orthometric map of the area which can be seen on the right against a black background. This can be rotated in 3D. It is georeferenced and can be superimposed against a symbolic map or a satellite view of the area. It can be exported and transferred to a GIS program as a raster layer. In the inset on the upper left of this frame is a user point of view similar to a Google Street View. This can be rotated or zoomed to look around the landscape, and the viewer's position can be modified by clicking anywhere on the map. The two views are synchronized. This is great for inspecting the landscape and understanding the context of the site. At this point, the only problem is the 5.7K resolution distributed across this entire spherical view is not as high as we might like. In the screen capture on the right, I've switched the positions of the map and the user point of view, and my view is looking at a point on the ground where there are actually some bones exposed in the eroding side of a stream bed. Unfortunately, even after zooming in, it's very difficult to see these from the image at this resolution. We are investigating ways to improve this performance through both hardware and methodological changes. Traditionally, 3D reconstruction in archaeology relies on meshing, creating a skein of triangles over a point cloud. While effective for buildings, meshes struggle with landscape which is full of thin geometry like tall grass, porous coral rocks, and palm fronds. We utilize a breakthrough technique called 3D Gaussian splatting. Think of this not as a solid shell, but as clouds of millions of tiny semi-transparent splats or blobs. Each splat contains data on its position, its size and orientation, its transparency, and its color. This means as you move your head in VR, the splats change how they reflect light, mimicking the way real-world surfaces look from different angles. This is a massive leap over older neutral radiance fields because it allows for real-time rendering. We aren't just looking at a static photograph. We are calculating a volumetric world that looks soft and natural rather than jagged or melted look that's seen in traditional archaeological meshes. To validate our choice of technology, we performed a side-by-side comparison between traditional mesh reconstruction and 3D Gaussian splatting. If you look at a traditional mesh of a historic site, you'll often see holes where software couldn't find enough matching points, especially in shadows or shiny surfaces like wet rocks. Meshes also struggle with transparency. They try to turn a blade of grass into a solid block of concrete. As you can see in our results, the splatting method captures the fuzziness of the Caribbean brush and the complex textures of the eroded soil far more accurately. However, we did find one trade-off. Meshes are better for taking exact geometric measurements of a wall or a building. Therefore, we proposed workflow is multimodal. We use splatting to create an immersive world and the environmental context, and we use high-resolution photogrammetry for the specific artifacts. This approach ensures that we have both the atmosphere of the site and the scientific precision required for the archaeological measurements. A quick demo to compare between these two virtual reconstructions. On the left, you see the traditional mesh method. And on the right, the 3D Gaussian splatting. You can clearly see the more atmospheric presentation in the Gaussian splatting. We integrated our Gaussian splat models into the Unity 2022.3 engine. This was a significant technical challenge because Gaussian splats are computationally heavy. Our model for the Whites Bay well contains nearly 1 million individual splats. We targeted the Meta Quest 3 as our primary hardware. This makes it a tool that can actually be used in the field or in a classroom in Nevis. To achieve this, we used a custom rendering pipeline that optimizes how many splats are drawn at once. We successfully maintained a frame rate of 72 to 90 frames per second. In the world of VR, the frame rate is king. Anything lower than 70 frames per second causes sim sickness or nausea. By hitting 90 frames per second, we ensure that an archaeologist can spend an hour inside the virtual Whites Bay site conducting a virtual excavation without any physical discomfort. In conclusion, we've shown the results of the work done on the Caribbean island of Nevis documenting prehistoric sites threatened by development and climate change by generating digital twins using 360-degree cameras, photogrammetry, and Gaussian splatting. While the results look promising, we plan to return to Nevis this coming summer to collect more data and continue to develop the visualization pipeline to enable artifact identification and classification and immersive visualization in a virtual reality environment. I'd like to acknowledge and thank Professor Marco Menichetti and the San Jose State University Nevis 2025 archaeology team for the contributions they made to this and the ongoing project. If you have any questions about this work, please don't hesitate to contact me or Professor Vuthea Chheang directly. Thanks for your attention.